My name is Andre. I work in Uber in New York, and I was going to talk a little bit about overlay networking. And since it's going to be an introductional talk, so not much of a technical dive and something like that, but still should be pretty cool. So I guess I should stand here to click things. So the problem, right? Because if something new appears in the world, that means there is some problem first, and then people decided to try to fix it, right? So a little bit of history here. So some years ago, in data centers, there were normally only hardware, like bare bone servers, no virtual machines, no containers, no nothing, and it all worked pretty much okay. Packets were flowing in the network. There was IP, there was TCP and UDP, normal routers, normal switches, and everything just worked. But then things started to change, and virtual machines started to appear, and now containers is all around the world. So there appeared some problems that, I'll just stand here, some problems that the engineering community decided to address. So one of the problems that started to appear in data centers and in cloud provided data centers and things like that is the shortage of VLAN address space. So normally what you do in your data center is that you divide it into segments and you assign VLAN tags to each segment. And that's how you do, that's how you basically divide your data center into parts that may be logically separated or for security reasons, something like that. So VLAN as a protocol has a physical limitation of 4,094 VLAN tags. It's actually 96, but 2 of them are reserved, so it's 94. So that means in every single data center, basically, you can have only 4,094 separate segments tops, if you're lucky, because usually hardware doesn't even support that. So it's not really a problem if the only thing you have is like normal servers, and there's no virtual machines, no containers, no nothing at all. But once you start to virtualize your hardware, and every server starts to have hundreds or maybe even 1,000 virtual machines, or hundreds of thousands or even tens of thousands of containers, starts to be a problem, because if you want to separate the domains in your network with VLAN tags, you can't really do that because that's your limit. And if the data center is a cloud provided data center, you have hundreds of thousands, many tags to use for their needs to separate the network, and for example, some kind of front end, back end, database access layer, or front office, back office, something like that. So it just stopped working basically at some point. Another problem, which is kind of part of that, is the security and scalability problem of tagging with VLAN or with VLAN tags. So it doesn't really work because, as I said before, just not enough of them, and VLAN tags, they don't really provide the security that the engineering community wanted to. Another problem is the MAC translation table bloating. So in data centers, there are racks, and we have servers in the racks, and each rack has a top of the rack switch, and each top of the rack switch is supposed to learn the MAC addresses of each virtual machine, of each server, virtual machine, or container that is in the rack. So if you have like 20 servers in the rack, that's fine. If you have 1,000 virtual machines, it's kind of still fine, but not really fine anymore. If you have thousands, tens of thousands of containers, top of the rack switches will basically overflow the table, and what happens if the table is overflown is that it just stops learning MAC addresses, and it just waits for the expiration timeout and drops them over the table, and then learns new MAC addresses again. And the end result of that is that if one of the new containers is spawned and it tries to send some packet somewhere, the switch will just look at the table. It will see that there is no entry for that destination address at all, but the table is overflown. So what it will do is just flood the traffic into the network. Like basically, we'll do ARP requests on each drive, which is basically it will kill your network. And the last problem is that in these cases, for example, imagine that a customer in data center in the cloud provider data center had a few racks and an L2 segment that it worked with, and then because of the growth or something like that, this customer started to need more resources, more servers, and more L2 segments, more VLAN tags, something like that. And in this case, you just can't do anything at all because the maximum diameter of the L2 segment that you can have is your configured limit, the data center configured limit of the VLAN tag propagation, which is usually not that much at all. So considering all this, the engineering community decided that we have to do something about it, and this something is it appeared to be a new standard for this kind of networking. So one might ask that why a new standard? We have like 100,000 different networking protocols, and well, we can probably do something with them, right? But it never works with engineering, as you probably know, because we like to reinvent all the things all the time, over and over again. So engineering community reinvented all the things again. So just as a side note, what could have been done instead of that, for example, is that we have a protocol called MPLS, which is used in all data centers all around the world. It connects thousands of networks together, and it actually can be used to solve all these problems. But the reason for this protocol to not be adopted for this kind of issue was that it requires specialized hardware in the data center, and it requires, let's say, special engineers that know how to work with it. What's that? Somebody's calling us, I think. Okay, so it requires, basically, it's hard to configure and maintain. And mainly it's hard to configure and maintain because you can't really do it from software easily. Somebody's really calling. Oh yeah, actually, let's go back. So that was the reason given by the community that came up with all this overlay networking. Another protocol that supports basically all the features that we need to solve these before mentioned problems is GRE. And it actually is used in one of the standards for overlay networking called NVGRE. And it's supported by Microsoft, but for some reason it gained almost no traction in the world. And I think the only thing that supports it is OpenVSwitch, and I've never actually seen it in production anywhere. So maybe it's too young, maybe it's just broken. I don't know. And one other alternative is OTV by Cisco, and it works. It's about, I think it's about like 7 or 6 years old. But for it to work, you need to use Cisco hardware, and that means you have to pay a lot of money. And all these people from all the startups don't have any money at all, usually. So yeah, that's what happened again. We just reinvented all the things, and we put another layer of indirection on top of what we had, and that kind of solved problems. Well, hopefully it will work a little bit longer. So what's the solution? The solution is the overlay networks. So what is it? The idea behind overlay networks is to virtualize the network in such a way that it is decoupled from the hardware physical network completely. So there were many solutions in between which tried to kind of build on top of old protocols. For example, there was a thing called Q&Q, which is basically VLAN tags in VLAN tags and VLAN tags. It's still used, but it's not really useful for this situation, again, because it's hard to use from software. Kind of, it's kind of hard to build this kind of thing into, for example, Docker engine. But we ended up with this. So the overlay network is basically a something called MAC in IP, which means we will just encapsulate all our MAC frames into IP packets and just send it over the network we already have in the data center. And by doing that, we basically separate these two layers, right? We have some kind of physical transport layer that we had before that can transport IP packets all around our data centers and all that. But instead of using VLANs or anything else, we'll just use this network to only transport our encapsulated kind of APAC packets, right? So, for example, the VXLAN protocol, which is, as of now, the most popular for these kind of things, it encapsulates the MAC frames into UDP and just sends the UDP all around the place to build this overall network on top of the physical layer. And very important thing about that is because it's just an encapsulation technology that uses the underlying TCP and TCP/IP and UDP/IP protocols, it requires no special hardware at all. It still can kind of make use of this special hardware if you have it, and there are hardware devices that already knows how to handle VXLAN and how to do things about it. But if you don't have anything in your data center or a provider doesn't support anything like that, it's fine because it just works on top of software and you don't need anything else. The NVGRE, as it states from the name, is based on GRE, and it just encapsulates your Mac frames into GRE. The slight downside of that is that GRE is not TCP and not UDP, so it's kind of another layer 3 protocol. So you still need some kind of support in hardware to use it, but GRE is widely popular, and it's basically you can find it in any switch and any router. So that's kind of fine. And all these protocols, one of the main kind of features of these protocols is that instead of the VLAN tags that are only like 4K, they introduce a new tagging primitive. In case of VXLAN, it's called VNI, Virtual Network Identifier, which in this case is 24-bit, which means you can have 16 million virtual networks in your data center, and that's probably will pretty much cover any needs for a few years coming from now on, hopefully. Unfortunately, because of the software restrictions and the speed of CPUs and the speed of hardware and everything like that, you can't really have 16 millions now, but you can probably have a few millions, and I think it will actually work. So how does it actually work? So I've kind of borrowed this nice picture from a Cisco website. Doesn't really look good, right? It's kind of stretched. Okay, anyway, that's how it works. I'm going to explain. Hang on. So the normal operation of the VXLAN, as in it's already stabilized, it learned about all the peers, it knows about all the topology and everything like that. So basically that's how it will work after something that I'll tell you in the next slide. So the operation is pretty simple. So here we have one of the hosts which can be a virtual machine, an actual physical host, a container, basically anything like that. So if it wants to send a packet to another host on the network, it just takes the data you want to send, it puts it into normal IP packet, TCP packet, whatever it is, and puts it in a normal MAC frame, Ethernet MAC frame, and it sends to a VTAP. VTAP is this thing that was introduced by VXLAN. It's a VXLAN tunnel endpoint. It's kind of a virtual device. It can be implemented in software. It can be a hardware device. It can be part of hypervisor, anything like that. So it sends this packet towards the VTAP, which takes this packet and looks up into its translation table if it knows the destination MAC address. If it sees that the MAC address is local, it just basically forwards it back to this machine, and it's got dispatched to another virtual machine or another container. If it sees that it's not local and belongs to some other host, then it will encapsulate it into a VXLAN packet, which basically means that it will attach a VXLAN header, UDP header, an IP header, and a MAC header on top of it, and send it through your normal transport IP network. And slight problem with that is, as we heard, there's a lot of headers to be attached to it. So the overhead is about 50 bytes for each packet, and that's not really good if you, for example, send a lot of small packets or the traffic rate is very high. But we'll talk about this later. So this packet is traversing the network the usual way any other packet will traverse it, and it ends up in the VTAP of the other host or other container, and this encapsulation procedure will be reversed, and the packet will be delivered. So it's not very magical, as you can see. It's pretty straightforward, except for this multiple layering of headers and the overhead. So this is how it works normally when everything is already learned and all the topology is known to the overlay network. So as a side note, for example, the VTAP, the VXLAN tunnel endpoint, is implemented in Docker Engine, it's implemented in OpenVSwitch, it's implemented in VivNet, it's implemented in CoreOS FlannelD. They all are supporting that. And actually, it's not very true. They use the kernel module for VXLAN to do that. So, and there are also hardware devices by Cisco, by Arista, by Juniper that can act as VTAPs as well. So that would be a nice picture, and that would be actually good technology, if not this. So that's what happens when the network is starting, or when you're adding new peers, adding new containers, stopping containers, adding new virtual machines, or migrating them across the network. So the problem with VXLAN and NVGRE and all these protocols is that if you read the RFC, they have no notion of control plane at all, or management plane as well. So it's supposed that this information about where to send packets, where other VTEPs are, where the nodes, where the peers, it has to be kind of given them from outside somehow. So the RFC says that it's kind of, we'll just omit that and leave it as an exercise to the reader, as it's like a very easy exercise, but it's not, right? So there is a fallback in VXLAN standard that says that in this case, we'll just multicast things around the network. And if you worked with networks, you know that multicasting data center is like one of the worst nightmares of data center operators. So the idea behind this is that when the host A wants to send a packet to some host B with some different MAC address, and the VTEP that this host talks to, for example, the hypervisor or the VXLAN kernel module or something like that, doesn't know anything about this remote peer, what happens is that it will encapsulate this packet into a VXLAN frame, and it will multicast it to a multicast group that is associated with this VNI, the virtual network. And one thing about that is that you have to actually associate these multicast addresses manually with each VNI. So remember, I was talking about 16 million of them, right? So it's not really easy to do that, because that means I have to have 16 million multicast addresses to do that. So not only that, so since you have to send it into the multicast group that you manually associated with the VNI, you have to support multicast in your data center. That means you have to configure a GMP, PIM, or something like that to support multicast. And as far as I know, for example, when you start talking to the vendors about, hey, we need multicast in our data center, they're like, no, just go away. Or pay us money, something like that. So anyway, let's consider that we have multicast. In this case, the packet will be multicasted to the group that is associated with this VNI, and all other VTEPs for these VNIs and all other hosts, they will receive this packet, they will decapsulate it, and forward it to their peers. And one of the peers, in this case, this guy, number 4, it will see that, oh, this is my MAC address, so I'll just respond to this ARP request with my MAC address. So when this happens, the VTEPs 3 and 2 that receive this multicast datagram, they already know that MAC A, the source address of this resolution request, is there. So like so that VTEP 1 manages this MAC A, and once the host here responds with this to this ARP request, the VTEP 2 already knows the path back to VTEP 1, so we'll just unicast it back. And that sounds good, but that means that all other VTEPs will never know about the response. So we have to repeat this ARP request again and again and again if you want all the VTEPs to learn about the topology. So that's not really great, but that's how, for example, the normal VXLAN operation work in the kernel if you just do it manually. So yeah, control plane. So none of these protocols specify any control plane at all. So what happens usually is that all the implementations, like for example Docker or Flannel or something like that, they resort to use some kind of external shared state storage to store the topology. And it can be Zookeeper, it can be TCD, it can be Console, it can be something else. And as you might imagine, when you have Zookeeper or etcd or Console as a part of your network management layer, a control plane, that kind of calls for disaster. It will probably break, especially if it's Zookeeper probably. So yet that's how it's usually done now. There are a few enterprise solutions to this problem. For example, OVSDB, which is Open vSwitch DB, is a VMware protocol designed to manage Open vSwitches. It's open source, and there is open source implementation for client and server, but I've yet to see a kind of full stack solution that actually uses OVSDB to propagate topology across VXLANs in open source. I mean, it's a part of, for example, proprietary VMware hardware and software for money, but not an open source. There's EVPN, which is a BGP-based control plane, which is abstracted from the data plane, so it can be used with VXLAN. It can be used with anything else, and that's another way to do the control plane for VXLAN. But again, I've never seen it in open source or used in non-enterprise deployments. And then there is DAV, which is IBM full stack solution for this problem. It's based on VXLAN, and it has a special built-in control plane and management plane and all cool UIs and everything like that. But it also not really usable in open source world. So yeah, let's talk about the common implementation, since this is container-based, right? So let's talk about container things. So these are three major implementations for VXLAN and overlay networking. There are more, but this is what people usually talk about when they mention overlay networking. So the first one is the built-in Docker multi-host network, which is a part of Docker Engine, and you don't need anything else for it to work except Zookeeper console or etcd. So it's based on VXLAN. It uses the kernel module for VXLAN, which was merged in the kernel in 3.14. It has no fallback, so basically if you don't run 3.14 or you miss this module or something like that, you can't use it, and there is then there will be no multi-host network at all. Then there is WeaveDet, which is also based on VXLAN, but in this case it's based on the OpenWSwitch module in the kernel, OpenWSwitch data path, but it's basically the same thing. And it has a custom UDP-based fallback called Sleeve, which is basically the same thing as VXLAN with a slightly different packet format, but it runs completely in user space. And the control plane is built in, and I actually don't know what kind of built-in control plane it is. I mean, it's not any of those shared storages, but it works. And there is FlatLD by CoreOS, which is also based on VXLAN, on the kernel module. And it also has a custom UDP-based fallback mechanism, which is a little bit different from WeaveNet. We'll talk about it a little bit later. And it has a built-in control plane that uses etcd as a shared store for the topology information. I'm not going to talk about Docker much because it's extremely straightforward. It basically calls kernel to set up VXLANs, and that's it. There is nothing fancy in it. It's very straightforward. But I'm going to talk a little bit about WeaveNet. So WeaveNet, as I said, has two different versions of the overlay networking. So the normal mode is called Fast Data Path. It appeared, I think, a few years ago. So yeah, it just uses the OpenWSwitch kernel module and just talks to the kernel, and the kernel does all the things for it. The Sleeve fallback mode, it works in kind of a little bit unexpected way. So it uses PCAP to capture packets from your containers, which means that it basically runs TCP dump on everything. And it just captures packets, encapsulates it in its own packet format, and then routes it through the topology that WeaveNet learns by talking between the agents of WeaveNet. And these agents talk to each other with TCP, and they exchange topology information. And that's how all the agents know about the topology of the network. A cool thing about Sleeve is that it supports full encryption. Basically, that means that the whole traffic will be encrypted. That's probably a nice addition if you stretch your overall network across some kind of unsecure links or something like that, like over, I don't know, internet or something. And another cool thing about Weave is that it has all these other products in the ecosystem, like Weave DNS, that will register your containers with the built-in DNS so that you don't actually need to know all these IP addresses. You can just talk to the services using their names. It has Weave Scope, which is like this fancy introspection UI where you can see all the links and how data is flowing inside your network. And it has Weave Flux, which is basically like a routing layer on top of WeaveNet. And that's nice as an addition to whatever we already have. The FlanLD, the interesting part about FlanLD is, I mean, non-interesting part that it also uses VXLAN to do the kind of fast data path. The interesting part is that if you run infrastructure on top of AWS or GCE, then FlanLD has this special kind of backends to utilize the capabilities of AWS and GCE. So instead of building any kind of virtual overlay network in your topology, it will just call AWS or GCE infrastructure and set up the routes using the primitives that these platforms provide. So there'll be no encapsulation, no decapsulation. It will just work, and it's expected to be faster. And the fallback path is implemented using IPMask, which is basically it's based on IP tables, and it should be a little bit faster than TCP dumping all the traffic on every box. So the downsides of virtual networks, of overlay networks. So it's all good, kind of, since you can virtualize your network, you can build a separate network on top of your physical infrastructure, you can build many of them, you can compartmentalize every subsystem you have in your in your service, and that's pretty good. But there are a few problems with that, right? So the main problem, as I see it, is the load sharing. So normally, when we operate with the traffic in a data center, we try to utilize all the paths we can so that we can utilize the whole bandwidth that the network infrastructure provides. And to do that, we use things like ECMP, which is equal cost multipath, or LACP, which is link aggregation. So to do that, what happens is basically when a packet stream, for example, if it's TCP, arrives at a router or a switch, then the router does the basically it takes the information from the packet that it can take, like source address, destination address, source port, destination port, that kind of stuff, and it hashes it, and basically based on this hash, it picks one of the routes that is available to the destination. And if we have that, and for example, we have two hosts talking to each other and sending a lot of traffic each way, what happens is that based on these hashes of these components of the frame header, we can send these streams in different paths so that we can utilize the whole bandwidth that is available for us in the data center. So in case of VXLAN, we can't really do that anymore because VXLAN traffic from the point of view of the network is two VTAPs talking to each other. And both VTAPs use UDP to send the traffic, and they have the same port. So this is basically traffic going from one port. For example, the standard port for VXLAN is 4789. So it's 4789 talking to some other 4789. And if we have multiple hosts on both sides of these VTAPs, from the point of view of the network transport layer, it's the same stream. There is no difference at all. So it will be all sent to the one path. There are hacks around it already, like it always happens with computers. So, for example, there are Cisco supports kind of looking inside the encapsulation packet to see what the actual destination is. But that means that for every packet, we have to decapsulate and encapsulate it back on every hop, which is overkill. In case of NVGRE, it's actually a little bit easier because all the routers already support looking up, using the NVGRE key to do the load sharing. But NVGRE is kind of not really useful because nobody implemented anything like that in, for example, Docker or Flannel or something like that. So load sharing is kind of out of the table. Another problem is, as I said before, is multicast and the lack of control plane. So if you use Docker or Weave or FlannelD or something like that, it's not really a problem because they will do control plane for you using these very stable technologies like Zookeeper. But if you don't use it, then there is no other option except to flood the whole network with packets. Not the whole network, to flood the multicast traffic to the network every time you need to learn about a new peer or propagate information that the peer has gone or something like that. One exception is head-end replication, which is basically another hack invented by Arista Networks and Cisco, which basically makes your VXLAN implementation not non-compliant with the standard, but it helps because instead of multicast, it will just replicate. Instead of multicasting everything, it will just send normal unicast packets and replicate them further and further across the topology when we need to learn about the new peers or propagate information about the dead peer. Another problem is the overhead. So one case of overhead I was already mentioned, which is the bandwidth. So for each packet, we have 50 extra bytes we need to slap on it with all these extra headers, which might be fine if there is not much traffic going on, or if the packets are huge, for example, and we have jumbo frames and that kind of stuff. But that's not always the case. So what can happen is that we'll basically, also I have actually a good example for that. So for example, the WeaveNet will try to determine the MTU on the path of the between all the WeaveNet routers, and if it will see that MTU is not enough to slap on these extra headers, it will just silently fall back to this leave thing that is run completely in user space. So it's not really cool. And another thing is the CPU overhead, because normally when you run your network without any virtualization, there are a lot of things that are offloaded to the network card. And in this case, we can't really offload much because it's all encapsulated and virtualized. So the only thing we can do is to offload the like this upper layer when we talk between VTAPs, but everything in between, everything under that, we can't do anything about it. So the CPU overhead, there is a paper by VMware that where they try to measure the CPU overhead for the VXLAN, and it said that for big packets, whatever that means, it's like 5%, and for small packets, whatever that means, it's 50%. I think 50% overhead is a little bit too much. And the last downside is the traffic tromboning. So traffic tromboning is something that happens as a result of a feature of overlay networking. So one of the features that they give us is that since the network is virtualized, we can move hosts around the network physically without thinking about any logical topology change. So for example, we have a host running on, we have a container or a virtual machine running on one of the hosts, and we need to migrate it to another host because of resource shortage or something like that. So if we use overlay networking, it's really easy to do because we just move the container to another host and we'll still have the same IP address and everything like that. And that's pretty nice, right? Because, for example, using some fancy technology, we can actually migrate containers without even stopping them, and that's pretty cool because users will see no difference at all. Traffic will still go, and that's pretty awesome. So yeah, we can do that with overlay networking, but what will happen is that if the container goes from host A to host B, the VTAP for container will still be at host A because nothing changed from the point of view of the overlay networking. So what will happen is that the traffic will actually go to host A, and then to host B, and then to host A, and then back to the user. So again, there are hacks around it, which will make your implementation non-compliant with the standard. But it's just another kind of workaround. And another downside is the benchmarks, right? So this is how it actually performs, right? So the first, so these graphs, they show bandwidth between two containers and latency between two containers. So the row one is just you start two Docker containers without no virtual networks or whatever, and just send traffic between them. So in this case, that's basically the ideal numbers we want to have. So the bandwidth is about 100 megs per second, and the latency is about 100 milliseconds. So the second graph is weave sleeve, which is the fallback encrypted mechanism that will be silently enabled if your MTU is not matching or your kernel is too old or something like that. So as you can see, it basically destroys your network completely. Nothing works after that because your bandwidth will be more than 10 times less and your latency just goes up 4x. So, I mean, it is kind of networking, but it's completely not usable in production. Weave FDP is when Weave is using the kernel module to do all the forwarding. So basically, what it does in this case, it won't TCP dump anything. It won't do any forwarding. It will just talk to the kernel, configure all the interfaces, and the kernel will do everything for you. So yeah, in this case, it's kind of comparable to raw performance, and this is actually pretty nice. The FlannelD UDP is the fallback for FlannelD. Oops. It performs a little bit better than Weave Sleeve because it doesn't TCP dump stuff. So I was going to say the bad word. So it uses IP tables to do things for you, and it's a little bit faster, but it's still unusable. I mean, it's probably usable for things like staging or testing or something like that, but for production deployments, it's completely not usable at all. And the last one is the FlannelD VXLAN, which is the FlannelD way to use the kernel module. So it's a little bit better than the Weave one because it uses the VXLAN module directly, while Weave FTP talks via the OVS data path first. So that's my guess. That's why it's a little bit better. Or maybe that's just the measurement error. They look completely the same to me, more or less. So yeah, that's the benchmarks. The Docker one is exactly the same as the FlannelD VXLAN, by the way. So I just omitted that from the graph to feed it in. And I've seen the 10 minutes mark, so I'm just going to end it and answer your questions.
They're doing the Zookeeper for control plane or whatever. Are they essentially like re-implementing like BGP and just keeping the BGP table like in Zookeeper and sharing it?
It's
something smarter.
It's actually dumber than that. So it's basically a shared ARP table.
Okay.
It just maps IPs to MACs, and for each MAC, it's a MAC of a container of VM or something like that, and IP is the VTEP IP, and that's all. There's nothing else. There are different contraplane implementations, like for example EVPN, which actually is based on multi-protocol BGP, but it's kind of it's not an RFC yet. It's not really implemented anywhere apart from proprietary Juniper hardware, Cisco hardware. Should we do like microphone?
Project Calico, did you mention that?
No, I didn't. So Project Calico is not overlay networking. That's why it's not in this presentation. So Calico is basically, these people kind of managed to sell BGP for money, basically, because what they do is that they put BERT, which is the BGP daemon, on every host, and they have a contraplane that basically syncs these BERTs together, and they just do like normal network routing, but with a fancy UI and all these kind of things. But it's not overlay networking. It actually uses your actual physical data plane to forward traffic. There is no overlays, no encapsulation, no decapsulation.
Okay.
Looks like there are no more questions. No, there is one more question. I can hear. So it's I just ran it on my own on this computer. It's two Docker containers running in a virtual machine. Nothing fancy. I mean, probably if I run it using like actual hardware, actual service numbers will be different in scale, but not relatively, because that's the same thing more or less. I mean, maybe there will be some difference, but to have like a broad picture of what the actual performance is, I think that's good enough. We can rerun it with actual hardware. I think so. Even though the technology is a few years old already, VXLAN, for example, I think that it's just not really kind of done, the contraplane part. So the normal way to do it, as I said, is you just use some kind of etcd and whatever. And everybody else who comes up with this new overlay network implementations based on VXLAN, they do the same thing. Just put on some etcd in the middle of that and just share the state. I mean, probably the EVPN will be better because it actually uses your actual networking routing protocols like BGP, for example, to propagate this information between peers. And BGP is kind of proven to work by decades of actual production, but it's yet to be implemented in such a way that everybody can actually use it, because as I know, every time people start to talk about BGP, it's like this is something like magic, and let's not really talk about that. It's something in network. If we touch it, everything will just break down. So maybe there should be some kind of like more open information about how these things actually work, so that the open source community can take this and build it into their own products. Because, I mean, for example, as this gentleman said about Calico, right? So Calico actually did that, but they took BGP and put it so kind of deep behind these layers of abstractions and fancy UIs that it's not really clear that they just reused the same old technology, which is like 25 years old, to do these things. Yeah? Oh, that's good. I didn't know that. Yeah. Yeah, but that depends on how they actually built it, right? So, as I know, for example, GCE, they don't actually use VXLAN for the virtual networks they provide you with. And they use something like VPLS or something like that. I'm not really sure about that, which is supposed to be faster. I mean, it's already fast enough when you use kernel module. You lose like 5 to 10% of bandwidth and you gain 5 to 10% latency. But if it's really, really critical, then these specialized backends for GCE and AWS might prove to be more effective than that.